The universe stops rendering when you stop looking. It's not a metaphor. The stars stutter. For a heartbeat, Orion flickers like a buffering video, then steadies. You hold your breath. Was it you or the sky? Here's the thing. What if reality doesn't load all at once everywhere, but only where and when it's needed? Locally. Efficiently. Tonight we're testing a sharp idea with real stakes. The universe might render just enough to keep your story consistent. The boundary that matters isn't a wall of brick, but a limit of information. The cosmic horizon, the farthest map tiles loaded in your instance. From quantum labs to the edge of the sky, we'll ask, what changes when we look away? The map that ends, what the cosmic horizon really is. To understand where the map ends, we need to separate two edges people often mash together. There's the particle horizon and there's the event horizon. They sound similar. They aren't. The particle horizon is the farthest light that could have reached us since the Big Bang. Today, that sphere is about 46.5 billion light-years in comoving distance. Wait, 46.5, not 13.8. Here, the trick. The universe expands while light travels. So a photon that left a nursery galaxy when the universe was young has been flying through space that's stretching under it. The path length today isn't the light's travel time. It's the current spacing of the markers along the way. That's why you get a larger number. The map doesn't have an edge like a cliff. It has a limit set by time and expansion. Now the event horizon is colder. Stand in our patch and ask, what events anywhere can ever send me a signal if I wait forever? Dark energy pushes the answer inward. In a universe where expansion accelerates, there's a boundary beyond which even light aimed our way now will never reach us. That's the event horizon. It's not a wall. It's a promise that some stories will never cross into our lives. Here's where it bends your brain. Galaxies beyond a certain distance recede from us faster than light. That doesn't break relativity. Space itself expands. The speed limit binds motion through space, not the growth of space. So you get a universe where recessional speed can exceed c and signals still obey the rules. Your local light cone, the set of events you can affect or be affected by, sits inside this larger stretching fabric. Horizons are the geometry of causality, drawn by expansion and measured against what light can actually cross. What nobody told you when you first saw those Hubble Deep Field posters is this: the edge of the visible universe isn't a painted dome. It's a time limit. Light takes time, expansion adds distance, and we sample a shell of histories. We don't see the universe as it is now. We see many nows, stacked by distance, with the farthest nows older than galaxies themselves. So why call it a map that ends? Because beyond the particle horizon, no light has had time to arrive. Beyond the event horizon, no future light will. That's causal disconnection. If you're thinking in render terms, that's an unloaded region, not because a programmer forgot to fill it in, but because no message can request it. No ping, no texture. If no signal can go there or come back, then for us, it's out of scope. Meanwhile, the shoreline moves. Yesterday's particle horizon is smaller than today's because light keeps arriving from just beyond our previous limit. We're watching an ocean tide of information roll in, one faint photon at a time. Survey teams plan like cartographers at a shifting beach. New instruments, deeper exposures, careful calibration, always pushing the fade where noise overtakes signal. They're not drawing continents, they're catching whispers. Here's a micro story. A grad student schedules telescope time to map a patch near the South Galactic Cap, empty enough to cut foreground dust, rich enough to catch high redshift galaxies. She triple-checks the guide stars, then watches the first frames come in. Cosmic rays pepper the CCD. Distant smudges float in. She doesn't know it yet, but one of those smudges sits a little closer to the particle horizon than anything in last year's catalog. It's not a new edge. It's just the next grain of sand added to our shoreline. Let's talk distances because words can trick you. Proper distance now means how far that galaxy would be from us if you froze expansion at this instant and measured with a cosmic ruler. Comoving distance scales with the expansion. It keeps markers fixed relative to the flow. Light travel time is just the number of years the photon has been flying. Those aren't the same numbers. When people say the observable universe is 93 billion light-years across, they mean a diameter in moving coordinates, not a simple outtake back of light-years as time. The map's units depend on which grid you pick. And no, there isn't a sharp boundary in the sky. There's no place where galaxies turn into static. What happens is flux drops, wavelengths stretch, sources redden and dim, and eventually even our best detectors can't dig signals from the noise. That instrumental edge sits inside the physical particle horizon and moves as we upgrade our gear. The physical limit sits beyond that, and it moves too, because the universe keeps aging. Here's the heart of the matter. We want to treat the cosmic horizon like a fence around a yard, but it behaves more like a bandwidth budget. Within our horizon, interactions are possible. Information can circulate, structures can form and talk to each other slowly, bounded by light. Outside for us is unaddressable, not fake, not absent, just permanently offline to our instance. If you're holding the simulation metaphor, fine. The world renders where causal contact can, in principle, ask for it. No contact, no load. And yet, while the big map stretches and the shoreline creeps, the small game plays by other rules. Down in the lab, reality sometimes looks like it's deciding what to be only when someone checks. That tension, cosmic smoothness versus quantum choice, sets up the next move. We've drawn the border of our map. Now we're going to look at who, or what, decides what fills it. The observer problem, quantum choices and collapsing possibilities. Down in the lab, the universe refuses to play classical. A beam of electrons hits a plate with two slits. On the screen behind it, you don't get two bright bars. You get an interference pattern, dark, like ripples crossing. Waves, so far, so good. But now you add a tiny detector at the slits to ask a simple question. Which path did each electron take? The interference disappears. The screen shows two bars. The act of extracting path information rewrites what lands. Here's where people leap to consciousness collapses the wave. Slow down. The experiment doesn't care who's watching. It cares whether which path information exists in principle. If the environment, air molecules, photons, a micrometer, leaks that information, the interference fades. That's decoherence. The world is full of observers, and most of them aren't conscious. They're stray fields, vibrating lattices, warm instruments. They snatch fragile quantum superpositions and push them into stable, classical-looking states. But what do we mean by collapse? Depends who you ask. In Copenhagen-like views, the wave function is a tool for predicting outcomes. When a measurement happens, you update the tool to match the result. No deeper mechanism offered, don't ask, just calculate. In many worlds, nothing collapses. The wave function evolves smoothly, and measurement entangles you and the apparatus with the system. You end up in branches where each outcome is realized. The interference vanishes locally because you can't talk across branches. In cubism, the wave function is personal. It encodes your expectations. Observation updates belief. These aren't idle labels. They shape what you think rendering even means. Let's keep this concrete. Decoherence says the environment singles out preferred states, pointer states, that survive the noise. Position of a dust grain, orientation of a pointer, current in a superconducting loop. The timescales are brutal. A micron-sized dust particle in air decoheres in about 1031 seconds for position superpositions larger than a wavelength of light. That's functionally instant. Macroscopic stuff stays classical because the universe won't stop measuring it. This is the plant from earlier. Selection isn't rare, it's relentless. So does the lab prove the universe renders only on demand? Not exactly. The lab shows that acquiring information kills certain interferences. It shows that outcomes appear definite because branches stop talking. It shows that being looked at, in physics terms, is just interacting with enough degrees of freedom to make history separate. Consciousness doesn't enter the equations. Entanglement does. If you hold the rendering metaphor, swap observation with information flow. The world renders. when information about alternatives becomes locally available and effectively irreversible, when erasing it would cost energy and leave detectable heat. Here's a micro story. A student aligns a delayed choice experiment. Photons pass the slits, then later, a choice is made to erase or preserve which path information. The pattern on the screen depends on that late decision. No signal goes backward in time. What changes is whether histories are recombined or kept separated. The student stares at the plots and whispers. It's like the past waits for the question we're able to ask. The advisor nods. It waits for the context. Now bridge up a scale. Can the same logic shape galaxies? You're not measuring a star with a lab detector, but the star is bathed in photons, gas, magnetic fields, gravity. It's coupled to a background of microwave photons, to dust, to neighbors. The cosmos is a giant environment. Decoherence at cosmological scales says the expanding background selects stable classical variables, density contrasts, curvature perturbations, out of primordial quantum fluctuations. That's einselection on a sky-sized stage. What looks like rendering is the universe locking in choices through interaction, not waiting for eyes. Still, there's a sharp stake here. Is observation special? If you demand a conscious mind, you've left physics and entered metaphysics. Every successful quantum device we've built works without minds at the point of interaction. A photodiode flips. A superconducting qubit dumps a photon into a cavity. A cosmic ray hits silicon. Information moves, interference dies. If information transfer is enough, then the rule is cheap. No magic, just entanglement growth and entropy bookkeeping. But there's a cost. Landauer will show up later with an energy bill for erasing information. For now, notice the pattern. The universe avoids keeping track of the impossible. You can't build an interference pattern if which path leaks. You can't signal outside your light cone. You can't see beyond your horizon. The same theme repeats, selection by constraints. Here, S where it nudges our metaphor. If outcomes get fixed where and when interactions spread information, then rendering is local and context-dependent. Not a central server deciding frames, but a network that stabilizes facts when enough links form. And because decoherence times are brutally fast for big things, your everyday world looks crisp by default. The mystery isn't why it's classical. It's how anything stays quantum long enough to matter. Hold that frame. The lab taught us that selection burns possibilities into facts when information escapes. Next, we'll ask how the cosmos might be running an efficiency play, minimizing what it keeps explicit, compressing what can be inferred, and budgeting the cost of information itself. Efficiency as a law, cosmic minimalism, and the energy ledger. If observation is information flow, then there's a price list taped to the back of reality. The universe is thrifty. It spends only when it must, and it compresses whenever it can get away with it. Start with entropy and the way we actually describe systems. We don't track every molecule in a room. We use temperature and pressure. That's coarse graining, keeping the variables that matter for outcomes, discarding the microscopic clutter. And here's the kicker. The macroscopic laws we trust, like thermodynamics, emerge because so many microstates map to the same macrostate. Efficient descriptions win because the world doesn't need the rest for predictions at our scale. Now bring in Landauer's principle, the bookkeeper's favorite line. Erasing one bit of information costs at least kT ln2 of energy dissipated as heat. It's not a metaphor, it's a measured bound. A memory reset in a computer dumps heat. A demon trying to cheat the second law pays his tab at the eraser. Translate that. Information isn't free. Losing track on purpose, resetting, compressing, overwriting, has an energy toll. Any rendering scheme that creates, stores, or clears bits is pinned to physics. What about the universe itself? There's an eerie hint in the holographic principle. Black hole thermodynamics tells us the entropy, the number of possible internal configurations, scales with the area of the horizon, not the volume inside. 1/4 of the area in Planck units gives you the bit count. That's so strange it sounds like a parable. The boundary knows more than the bulk. In lab-grade theory, add SCFT makes that literal. A gravitational world in the volume is exactly encoded by a quantum theory on the boundary. Our universe isn't de Sitter, so we can't copy-paste, but the pattern is loud. Count bits on surfaces, not in volumes. If bits scale as area, full resolution everywhere becomes absurdly expensive. You don't store every voxel's microstate in explicit detail. You keep boundary data and let bulk behavior be an emergent, efficient consequence. That's compression. Not sloppy, not lossy in the predictive sense, but minimal. The state you need is only as detailed as the questions you can physically ask. Here's an analogy with teeth. In software, lazy loading fetches assets when a player walks into a region. In physics, sparsity and symmetries cut the cost. Fields are smooth over scales, interactions have ranges, correlations fall off with distance, gauge redundancies hide wasted description. You never paid for every pixel. You paid for modes that carried energy and information across your horizon. Everything else stayed on the shelf as potential, not instantiated bookkeeping. Bring back Landauer and ask about the ledger at cosmic scale. Every time information is irreversibly recorded, when decoherent spreads and alternatives can't re-interfere, you've effectively allocated bits to classical history. You can't unspend that without a matching energy cost. Erasing is heat, storing is entropy. The universe chooses to let most details wash out, keeping only robust, redundant records, multiple photons bouncing off a chair, many molecules carrying the same trace. Redundancy sounds wasteful, but it's how facts become objective. Many witnesses, same story. Now stack this with the horizon. If the maximum number of bits inside your patch scales with its boundary area, then there's a hard ceiling on how much distinct detail can be physically present and retrievable within your worldline. You're living in an instance with a storage budget written on its edge. Try to imagine full fidelity everywhere, all at once, and you run straight into the bound. There's another efficiency play hiding in entropy and coarse graining, effective theories. You don't simulate quarks to model airflow over a wing. You use Navier-Stokes within a domain of validity. The cosmos does the same. Long wavelength modes govern structure growth. Short wavelength noise averages out. Inflation stretched quantum jitters to cosmological scales, but even then, only specific combinations survived to the microwave sky. The rest got smoothed, packed into parameters, compressed into a handful of numbers. Spectral index, amplitude, baryon density. Minimal inputs, maximal reach. Here's a micro story. A team running a galaxy formation simulation fights memory limits. They can't resolve every star, so they build subgrid models, rules that stand in for unresolved physics. Feedback from supernovae isn't simulated per blast. It's injected as heat and momentum according to calibrated laws. Critics grumble. Then the results match observations better than brute force versions did. The lesson lands. The right compression preserves what matters. But there's a cost to every shortcut, and physics forces honesty. Landauer says you pay to forget. Holography says you store on the edge. Thermodynamic says high-entropy states are typical, so order must be local, engineered by gradients and flows. If a rendering metaphor helps, use it like this. The universe instantiates only the correlations that can be accessed and preserved within horizons, encodes them redundantly for stability, and lets the rest remain implicit in symmetries and constraints. Not hidden by a programmer, but unnecessary to the questions any observer can physically pose. Hold that ledger in mind. Efficiency isn't an aesthetic, it's a survival trait baked into the laws. And just when we thought the budget was comfortable, a new telescope stared deeper and the timelines got tight. The early light that shouldn't exist, JWST's galaxy surprise. Then JWST opened its eye and the early universe looked crowded. Within months, preprints lit up with candidates at redshifts 10, 12, even beyond. Translation: we were seeing galaxies as they were a few 100 million years after the Big Bang, and some of them looked mature. Too bright, too massive, too structured for their age. Timelines we'd sketched with comfortable margins suddenly felt tight. Here's why that matters. Our standard model of cosmology, Landauer, lays out a growth plan. Tiny fluctuations seeded during inflation grow under gravity. Dark matter collapses first, making halos. Gas falls in, cools, forms stars. Feedback from supernovae and black holes regulates growth. The result is galaxies that assemble over billions of years. At redshift 10, you expect small, clumpy blue systems with modest stellar masses. JWST's early photometry hinted at objects with stellar masses of 1 billion suns or more and star formation rates that implied rapid assembly. If true, that compresses the schedule. Before you yell broken model, take a breath. First look photometry is slippery. You're fitting spectral energy distributions with only a handful of filters. Bomber breaks can masquerade as high redshift. Dust can redden a lower redshift galaxy into looking distant. Emission lines can boost brightness in ways templates miss. Teams race to secure spectroscopic redshifts, clean fingerprints from features like Lyman alpha breaks to confirm distances. Some candidates slid down in redshift with better data, others held fast. The picture got messier, not simpler. Meanwhile, simulators started sweating. If even a fraction of those early massive candidates were real, star formation had to be more efficient in dense, pristine environments than we'd baked in. Metal-free gas cools differently. Fragmentation can be wild. Massive stars form quickly, die quickly, and pour energy back into the gas. Black holes might seed earlier or accrete faster. Feedback recipes tuned on later epochs might not port cleanly to the first few 100 million years. Subgrid models, our compression tricks, needed new terms. There was also an instrument twist. JWST's NIRCam sees with exquisite sensitivity and resolution, but the early universe is small on the sky and faint per surface area. Surface brightness dimming is brutal. Something stretched by redshift loses brightness as 1 plus Z4. Yet some early candidates looked surprisingly large in angular size for their redshift, or packed more light per area than expected. That raised eyebrows. Were we biasing our samples by picking the brightest outliers? Were we lensed by foreground structures more often than we realized? Gravitational lensing can magnify and stretch distant galaxies, making the exceptional seem common if you don't account for it carefully. As spectroscopic follow-up improves, several masses and sizes continue to move toward more conservative values within Landauer allowances. Here's a micro-story. A small team working nights in a windowless room pushes through stacked exposures from a deep field. The Pi bets a good bottle of wine that their brightest object will drop to Z tilde 5 once they get spectra. The postdoc smiles, shrugs, and says, "I hope you like cheap Merlot." Weeks later, the spectrum comes in. The break is clean. The absorption sits where early hydrogen should sit. The object stays at high redshift, though its inferred mass ticks down after better modeling. The lab cheers, then groans. Their toy universe just got more complicated. What does this have to do with rendering and efficiency? Think in budgets. The universe doesn't get to violate causality or energy bookkeeping to fill in detail we find surprising. If early galaxies are more common or more evolved than our priors assumed, there are only a few levers to pull that respect the ledger. You can push star formation efficiency up in dense halos. You can alter the initial mass function so more massive stars form early, front-loading light. You can tweak feedback couplings so gas turns into stars before winds quench it. Or you can acknowledge selection effects. We're preferentially seeing the luminous tail because those are the ones we can see. There's also the possibility that our cosmological parameters shift within allowed uncertainties. The matter-power spectrums tilt, the amplitude sigma 8, the baryon fraction. Nudge those and small-scale structure grows a bit faster. Not a cheat, just a retune within error bars as datasets update. That said, the core Landauer scaffolding has survived rough tests. The cosmic microwave background's acoustic peaks, baryon acoustic oscillations, lensing maps, and primordial abundance measurements. You don't throw that away because early snapshots surprised us. You integrate the surprise. Here's where the rendering metaphor holds its weight without overreaching. JWST doesn't force the universe to invent galaxies to satisfy a camera. It exposes where our compression, our assumptions, was too aggressive. We'd summarized complex early gas physics into a few parameters. The data said not enough. So we spend more bits, more detailed models of cooling, starbursts in metal-poor gas, early black hole growth, radiative feedback in clumpy media. The map didn't glitch, our subgrid did. One more tension to park for later. A few early candidates showed odd sizes and surface brightness profiles that didn't line up cleanly with simple exponential disks or spheroids at that age. Some of that will wash out with better deblending and lens models. Some of it might point to early mergers shaping structure fast. And some of it might be a reminder that what we call galaxy at Z12 isn't the same creature as at Z1. Names compress. Nature resists, and follow-up will sort genuine outliers from selection biases. The stakes remain sharp. If the early timeline is tighter, then our efficiency story isn't optional, it's required. The universe had to build complexity quickly using minimal inputs and hard constraints. That's not sloppy rendering. That's a system leaning on symmetries, fast channels, and redundancy to stabilize facts early. We'll carry that forward as we step into places where the universe looks empty, voids and cold spots, and ask whether absence is a flaw or the cleanest kind of compression. Voids, cold spots, and missing texture packs. Elsewhere, the sky looks like someone forgot to paint. You swing the camera to the Boötes void, a region hundreds of millions of light years across with almost nothing in it, and your first thought is, under-rendered. A missing texture pack. But get this straight, emptiness doesn't mean error. It can be exactly what you expect when initial conditions ripple forward. Start with the cosmic web. From tiny quantum jitters stretched by inflation, gravity amplified slight overdensities into filaments and nodes, and it evacuated the spaces in between. Matter flows out of shallow valleys toward growing peaks, and the carved-out regions puff into voids. The biggest voids, like Boötes, are rare but statistically allowed in lambdictum. You run enough realizations of the initial power spectrum, and a few huge hollows pop up. They look like gaps in a painting because our eyes love uniform coverage. Nature prefers contrast. Here's a micro story. A survey team plots galaxy redshifts in a wedge of sky and watches the dots thin out, then nearly vanish. Someone jokes the instrument died mid-scan. The instrument's fine. The universe just left that volume empty. A few lonely galaxies haunt the interior. Most cling to the walls the way lights at night trace a city's highways while farmland sleeps dark between them. Under-rendered. No. Rendered as absence. Then there's the cold spot in the cosmic microwave background. A patch a few degrees wide that's noticeably cooler than average. The CMB is our oldest light, coming from when the universe cooled enough for electrons and protons to bond and photons to travel freely, about 380,000 years after the Big Bang. Across the sky, tiny temperature variations map density ripples. The cold spot is odd because it's big and deep. Some argue it's just a statistical fluke, a tail-end lump in a Gaussian field. Others point to the integrated Sachs-Wolf effect. As photons cross large evolving structures, they can gain or lose energy. A giant supervoid along our line of sight could leave a cooler imprint. Surveys did find an extended underdensity in that direction, but whether it's enough to cause the whole dip is still debated. Current analyses leave room for a modest anomaly without overturning Gaussian initial conditions. Notice what's happening to our metaphor. A missing texture implies a bug, a place the engine forgot to fill. But the physics explanation says emptiness can be a feature. Voids aren't just holes, they're laboratories. Galaxies inside them evolve with fewer interactions, less harassment, quieter inflows. The rules of the game are the same. The starting conditions are different. Compression would favor emptiness where correlations don't need to be stored because there's nothing to correlate. A blank region costs fewer bits. Stakes matter here. If you're hunting for breaks in the code, anomalies are tempting. You want the smoking gun, the glitch that says simulated. But you can fool yourself if you don't weigh probabilities right. In a universe this large, the far tails of distributions will show up somewhere. Rare isn't impossible. When you see a supervoid or a cold patch, the first question is who forgot to render. It's how often should this occur if the model is true? If the answer is occasionally, you take a breath and keep going. There's an irony worth sitting with. Voids carry less information than crowded nodes. If the holographic whisper is right, that boundaries count, the empty interior doesn't demand storage. What needs encoding are the walls, the filaments, the patterns at the edges. That's boundary-driven economy. You don't waste bits detailing uniform nothing. You spend where gradients live, where signals can propagate and be measured. In that sense, the cosmic web looks like a smart compression, sharp where it matters, smooth where it doesn't. At the same time, the cold spot forces discipline. If it's beyond what inflationary statistics allow, then something about the initial save file needs revision. Maybe inflation wasn't perfectly simple. Maybe there were features in the potential or relics from pre-inflation physics. Or, yes, maybe a giant late-time structure stacked along our line of sight is doing more work than we thought. Distinguish anomaly from expectation without hyping either. That's how you keep trust with a sky that doesn't owe you clarity. Here's another micro-story. A graduate student builds mock skies, injecting fake voids into simulated large-scale structure and ray-tracing CMB photons across them. She tweaks profiles, depth, sizes, and watches the temperature imprint shift by microkelvins. The numbers drift toward but don't quite reach the observed cold spot. She sends the plot to her advisor. Close, not enough. The reply comes back. Good. That means we're measuring. And this loops us back to boundaries. Voids, cold patches, filaments, they all speak in the language of light. Photons ferry the evidence. If nothing outruns light, then the shape of emptiness is set by what light can cross and what it can't. Where signals can't go, nothing can be asked. Where signals skim edges, boundaries matter most. Under-rendering isn't the right frame. Latency is. If you can't send the request, you can't expect an answer. Which is why, to see how far that rule goes, we have to follow light to its speed limit. Latency of reality, the speed of light as a hard cap. While that debate over void simmers, the real arbiter of what can be asked and answered is speed, specifically, the speed of light. C isn't just a number, it's a contract. It caps how fast information moves, which means it caps how quickly reality can coordinate itself across distance. If you think in render terms, C is your maximum frame sync rate for the universe. Start local. Your light cone is the set of events you can influence or be influenced by. Draw a point for you, then a cone opening forward in time for what you can touch, and a cone opening backward for what could have touched you. Anything outside those cones is off-limits. Not later, not with better tech. Off-limits in principle. That's latency baked into geometry. Space and time mix so that any path trying to outrun light gets pushed outside the cones and loses causal contact. Now scale up. Expansion stretches the grid itself. Galaxies don't rocket away through space faster than light. The distances between comoving markers grow. That's why recessional speeds can exceed c without breaking the rule. You still can't send a message faster than light to catch a fleeing galaxy if the expansion between you grows too fast. The metric gives you horizons because even a photon sprinting at c through the local fabric can't make headway against the global stretch. That's where the event horizon shows its teeth. Beyond it, no signal you send now, not even light, will ever arrive. Meanwhile, something else is happening across town in the gravitational sector. Gravitational waves ripple at light speed too. When neutron stars collide 100 million light-years away, the space-time tremor that eventually whispers through a pulsar timing array left long before we were born. Those arrays are patient ears. They watch for tiny shifts in the ticking of millisecond pulsars, searching for nanohertz waves that take years to cycle. It's a human lesson in latency. You set the experiment, then wait for the universe to answer on its schedule. Here's a micro story. A team calibrates a radio telescope at 3 a.m., sipping lukewarm coffee, chasing picosecond jitters in pulsar pulses. They know a wave, if it exists, will show itself as a correlated drift across the sky's clocks. Months pass. Then a hint, a common spectrum process. They don't claim victory. They add stations, extend baselines, push noise down. The signal strengthens. If it holds, it's proof that even gravity talks at sea, within the same horizon logic that hems in light. Latency isn't just delay, it's structure. Think of the cosmos as a network with finite bandwidth and bounded round-trip times. You can't coordinate a galaxy cluster instantly. Filaments form because gravity's pull adds up over time, not because distant masses negotiate outcomes in real time. Causal patches evolve semi-independently, and only where light and gravitational influence have had time to shuttle information do you get synchronized stories. Where the ping time is longer than the age of the system, the conversation never finished. That's not a glitch, it's the design constraint. This decision would haunt our expectations because it means global now is a myth. There's no universal present that renders in one sweep. Each observer's slice of spacetime is stitched from signals that actually arrived. Your now includes a star as it was years ago, a quasar as it was billions of years ago, and your own hands as they are. Reality is a mosaic assembled at light speed, with expansion stretching the tiles. If no request can be sent, no response must exist for you. That's the stakes line. You can't demand a pixel where no signal can, even in principle, fetch or verify it. In a bandwidth-limited, latency-bound universe, rendering is just the stabilization of facts within reachable cones. Outside, the best you get are priors, symmetry arguments, statistical expectations, consistency constraints. The map beyond your horizon isn't blank, it's inferred. It carries no more detail than your physical channels can justify. There's a flip side that makes the world generous. Within horizons, facts get broadcast redundantly. Photons scatter off a table into countless directions, encoding the table's location and color into many independent channels. That redundancy is how you and I agree on what's there without sharing minds. It's also why the energy ledger stays balanced. Creating objective facts is copying, not inventing. Copying takes time at sea and leaves trails you can cross-check. One last connection to carry forward. Photons and gravitational waves obey the same boundary logic. Both respect light cones. Both define what can be known and when. If horizons are interfaces, these are the messengers that patrol them. And if latency rules reality, then the universe didn't forget to render your far field. It's still in transit. Pixels in the dark, holography, Planck scales, and discreteness. Boundaries keep showing up, so the next question is obvious. Underneath the smoothness, does spacetime come in pixels? People point at the Planck length, about 1.6 times 1035 meters, and the Planck time, about 5.4 times 1044 seconds, and say, there's your grid. Careful. Those scales mark where our current theories stop making reliable predictions, not a proven lattice. They're thresholds that say, new physics lives here, not rulers etched into reality. Still, black holes hint at something radical. Take a black hole's event horizon and ask how many possible internal configurations it could hide. The entropy, the count of microstates, goes like the area of the horizon, not the volume inside. 1/4 of the area measured in Planck units. That area law isn't a vibe. It's a precise relation pulled from thermodynamics and semi-classical gravity. It says boundaries carry the bookkeeping. However you encode the interior, the maximum information scales with the surface. Holography turns that hint into a principle. In a set of theories we can solve, the anti-de Sitter ones, everything that happens in a gravitational bulk is exactly matched by a quantum theory living on its boundary. Geometry and gravity on the inside, quantum fields without gravity on the outside, 1-to-1. Our universe isn't shaped like those toy models. It's closer to de Sitter, and we don't have a complete holographic dual for it. But the area scaling lesson keeps showing up. Entanglement entropy of regions follows area laws in ground states. The guts of spacetime seem built from correlations that live on cuts and edges. If that's true in spirit for our patch, volumes might be effective. The inside behavior could be emergent from fewer degrees of freedom stitched along surfaces. That looks like compression again. You don't need a voxel by voxel ledger if the boundary, data, and consistency rules determine the bulk to the precision anyone can test. Not sloppy rendering, economical encoding. So where are the pixels? Experimentalists went looking. If spacetime had a grain, maybe high-energy photons from distant gamma-ray bursts would arrive out of order, with tiny dispersion depending on energy, like different wavelengths in glass. So far, null results. Photons across huge energy ranges arrive in step within tight bounds. Others tried interferometers to catch spacetime jitter, holographic noise, subtle positional fuzz at Planck scales. Clever setups set upper limits, but no confirmed wiggle. Smoothness holds, at least where we can measure. Here's a micro story. A small collaboration builds an instrument that cross-correlates laser beams to hunt for correlated flicker, noise that can't be blamed on the table, the air, or the mirrors. Months of data, careful subtraction, a winter of doubt. The final plot shows no excess. They publish a bound, not a discovery. It's not defeat. It narrows the map of what discreteness could look like and pushes candidate models to respect Lorentz invariance and known dispersion limits. Maybe the mistake is thinking pixel, the way a screen has pixels. Quantum gravity candidates, loop gravity, causal sets, spin foams, do talk about discrete structures, but they don't predict a simple grid. They predict spectra of areas and volumes, or partial orders of events, or networks whose coarse-grained behavior becomes the smooth metric we measure. The discreteness, if real, might be relational and hidden, not a visible checkerboard. Smoothness could be the signature of strong compression. Only long wavelength, low curvature modes propagate cleanly, and the microscopic mess averages out so well you can't shake a telltale shimmer loose. Black holes keep pressing the case for boundaries. Hawking's calculation made horizons radiate. The temperature, Gibbons, Hawking for cosmological horizons, Hawking for black holes, ties thermodynamic notions to spacetime itself. A horizon with a temperature has entropy. Entropy means microstates. Where do those states live? All roads point back to surfaces and entanglement across them. The interior is less a storage locker, more a region whose properties are encoded on or reconstructible from the edge, depending on the observer's access. There's also the page curve story waiting down the road. Information that falls into a black hole seems lost if you only trust Hawking's early calculation, but newer tools using quantum extremal surfaces show the entropy of the radiation rises then falls, as unitary quantum theory demands. That revival says the outward streaming quanticary correlations that, in principle, let you recover what fell in. Again, the surface ledger knows the tale. Boundaries tally, bulks comply. Notice how this changes rendering. We don't need spacetime to pre-store every microscopic detail in the volume. We need enough edge data and consistent rules so that any accessible bulk question has a definite, stable answer when asked. If discretization lives at Planck scales, it's hidden behind an extraordinary compression ratio. The lack of flicker isn't proof of continuity. It's proof that whatever the substrate is, it respects symmetries and cancels noise to a degree that beggars our instruments. Here's the stake. If bits scale with area, your world's maximum distinct information is finite for any finite horizon. A de Sitter, like Cosmos, hands you an entropy bound for your causal patch. Try to stuff more independent detail inside than that, and physics will push back, by thermalizing, by collapsing, by decohering and dumping heat. The horizon is less a wall and more a quota. And experiments haven't cornered the answer. No dispersion means one class of models is squeezed. No holographic jitter means another is pushed out. Yet black holes, entanglement, and thermodynamics keep whispering the same refrain. Boundaries encode, volumes emerge. If compression hides the pixels, then the universe's smoothness isn't a bug. It's the most efficient outcome allowed, which makes inflation's role as the first great compressor the next place to look. Inflation's pen, writing the first lines of the map. To see why the sky looks so well organized with so little time to spare, we need to go back before there was a sky in any normal sense. Inflation is the move that sets the board. For a sliver of a second, space itself expanded at an outrageous, accelerating rate, exponential growth that took a tiny, causally connected patch and blew it up to cosmic size. The payoff is simple to say and subtle to live with. Regions that look too similar to have ever talked at light speed actually did, before inflation stretched them apart. Here's the first consequence. The horizon problem, why the cosmic microwave background is the same temperature in opposite directions of the sky, melts. Those regions were neighbors in the pre-inflation patch. They exchanged heat, settled into near-uniform conditions, then inflation pulled them far beyond each other's light cones. What looks like an impossible coordination across billions of light years becomes a memory of a smaller, causally connected beginning. The second consequence is flatness. Curvature dilutes under rapid expansion the way wrinkles smooth out when you stretch a sheet. The universe we see is close to spatially flat because inflation ironed it. You don't need to fine-tune initial curvature. You need enough E-folds, enough doubling steps to wash it away. That's a compression trick, too. Take a messy starting state and leave behind only the largest scale, simplest features. But the move that matters for structure is the quietest one. Quantum fields fluctuate. Even in their lowest energy states, they jitter. During inflation, those microscopic jitters got stretched to macroscopic scales. Modes that started smaller than an atom became larger than a galaxy. When their wavelengths outgrew the horizon, they froze. Their amplitude stopped oscillating and imprinted as slight differences in density and curvature. After inflation ended, those frozen ripples re-entered the horizon and gravity went to work on them. You can hear the imprint in the cosmic microwave background's acoustic peaks. The early plasma of photons and baryons rang like a drum. Some ripples were caught at maxima, some at minima, some halfway. The pattern of peaks in the CMB power spectrum is a fossil sound wave chart, and it lines up with an origin in inflationary fluctuations, nearly scale invariant, slightly tilted, Gaussian to first approximation. A handful of numbers, the amplitude, the tilt, the baryon fraction, the dark matter density, describe it. That's inflation as a pen with a fine tip, writing a sparse instruction set that expands into a detailed cosmic web. Here's a micro story. A theorist scribbles ns approximately 0.965 on a whiteboard, the spectral index's value measured by Planck. Not exactly 1, slightly less. That small tilt says long waves have a bit more power than short ones, matching simple inflationary potentials. It's a whisper from a field we don't yet know by name, telling us the slope of the hill it rolled down. Now, honesty check. Inflation is a mechanism class, not a single theory. Many potentials can drive it. Some predict small primordial gravitational waves, a curl pattern in the CMB polarization called B modes. Experiments have chased that signal and set upper limits. So far, no confirmed detection. That squeezes models with large field excursions. Others survive. The search is ongoing, and that's good. It keeps the story anchored to what the sky allows. Subtle anomalies hang around the edges. The CMB shows a low quadrupole power compared to naive expectations. There's an alignment of low multipoles, an axis of evil in some papers. That might be noise, might be a hint. Hemispherical power asymmetry, maybe. These are low-significance curiosities that don't overthrow the core, but they do whisper that the initial conditions might carry features beyond the simplest toy. A bump in the potential, a brief interruption in the roll. Respect the whispers without mistaking them for shouts. Then there's eternal inflation, the idea that while our patch ended inflation and reheated into the hot Big Bang, other regions kept inflating, budding off bubbles with their own properties. It's a provocative edge case. If true, it seeds a multiverse where our observable domain is one pocket among many. Do we have evidence? Not direct. Some models predict collision signatures, bruises on the CMB from bubble-bubble contacts. Searches have turned up no solid scars. so we file it under speculative edges, consistent with the math in some regimes, unconfirmed by the sky. What inflation does give us with confidence is a data compression origin story. A tiny patch, smoothed and stretched, with quantum noise promoted to classical seeds. The universe didn't pre-store every detail. It recorded a minimal set of correlations and let gravity, radiation, and chemistry elaborate them. That's efficient encoding. The acoustic peaks are your checksum. The large-scale structure is your decompressed file. There's a practical stake. If the initial write was compact, then everything we see, galaxies, voids, clusters, comes from evolving those few parameters within tight constraints. When JWST surprises us, we tweak subgrid physics under those constraints. When we map a giant void, we test whether it fits a Gaussian seed field. When anomalies tease us, we ask if a small feature in the pen stroke could explain them without wrecking the peaks. The ledger stays balanced. The code stays lean. Hold this frame as we turn to black holes. If inflation wrote the first save file on a cosmic boundary, black holes test whether the universe keeps its records when matter falls off the map. Boundaries, entropy, information. They're about to collide in a decades-long argument that taught us how fiercely the cosmos guards its bits. The black hole accountant, information, firewalls, and retrieval. If inflation wrote a sparse instruction set, black holes test whether the universe ever throws the manual away. Stephen Hawking's calculation said black holes radiate, slowly, thermally, without memory of what fell in. That was the spark. Thermal radiation looks like noise. If a pure quantum state collapses into a mixed thermal soup, unitarity breaks. Translation: the cosmic ledger loses bits, and physics hates that. Here's the setup. A star collapses, crosses its Schwarzschild radius, and a horizon forms. Hawking pairs pop at the edge. One escapes as radiation. One falls in with negative energy, shrinking the hole. The outgoing quanta in Hawking's first pass carry no imprint of the star's microstate. After a long evaporation, you're left with radiation that doesn't encode the details of what fell in. That's information loss, not just ignorance. If true, quantum mechanics would need an asterisk. Then the community sharpened the question with a timeline, the Page curve. Don Page argued that if evaporation is unitary, the von Neumann entropy of the radiation should rise at first, because early photons are entangled with the interior, reach a peak around half the evaporation time, and then fall as later quanta carry away correlations that complete the story. So the curve must turn over. Hawking's original calculation gives a straight climb to the end. That mismatch is the paradox written as a plot. What nobody knew at the time was how to compute the curve from gravity. For decades, string theory, add SCFT duality, and toy models hinted that boundaries know more than they let on. From the boundary perspective, the ledger is never missing entries. The bulk is a way of talking about correlations on the edge. But the concrete gravity-side calculation arrived only recently. Using islands and quantum extremal surfaces, theorists showed that when you account for the entanglement structure properly, the fine-grained entropy of Hawking radiation follows the Page curve. Early on, no island, entropy rises. After the Page time, the island, the interior degrees of freedom that are effectively encoded in the radiation's entanglement wedge contributes and entropy falls. That's the accountant's stamp. Bits aren't lost. They're redistributed in a way gravity alone disguised. Here's a micro story. A young researcher prints the New Island papers, highlighter in hand, pacing a hallway at midnight. They sketch a horizon, a wavy line for the radiation region, a dotted line for the extremal surface. The math says the interior is now partly outside if you look from the right quantum vantage point. They grin, not because the paradox is solved in every detail, but because the curve finally bends the right way. Winning the ledger fight revealed a new one, the firewall. Almery, Maroff, Polchinski, and Sully pressed a consistency test. An old black hole with entropy past the Page time has its outgoing modes highly entangled with early radiation if unitarity holds. Yet smoothness at the horizon in semi-classical gravity pairs each outgoing mode with an interior partner just behind the horizon. Monogamy of entanglement forbids both. You can't be maximally entangled with two independent systems. So choose. Keep smooth horizons and give up unitarity, or keep unitarity and burn the horizon. Replace the gentle crossing with a searing firewall that breaks the equivalence principle. Physicists hate both options. They hunted for a third door. One path leans on state dependence and quantum error correction. In holographic codes, bulk operators behind the horizon can be reconstructed from different boundary regions depending on the global state. Entanglement isn't duplicated. It's encoded redundantly, like a secret that can be recovered by multiple coalitions without being copied. Another path invokes complementarity. No single observer can verify both the smooth horizon and the detailed structure of the radiation. For an infaller, the horizon is dull. For a distant decoder with impossible patience, the information is in the radiation. No contradiction appears within any one causal frame. Meanwhile, soft hair proposals note that conserved charges and subtle asymptotic symmetries could store additional data on the horizon, enriching the boundary ledger. Gravitational dressing and back reaction muddy the naive split between inside and outside. The moral keeps circling back. Surfaces no interiors. What you call inside is a story told from outside through correlations and reconstruction, bounded by what any observer can actually access. There's a practical sting, too. Could anyone actually retrieve the message? Hayden and Preskill framed the black hole as a mirror after the page time. Throw in a diary. After a scrambling delay of order m log m in Planck units, information starts to leak out at the hole's Hawking rate. In principle, with quantum control of the radiation and an absurd quantum computer, you could decode it. In practice, the ledger is safe from thieves because the work factor is astronomical. The universe is unitary, but not generous with shortcuts. Tie this back to our rendering metaphor. The black hole accountant says, no detail is ever deleted from the global record. When classicality forms, when decoherence spreads, when horizons hide regions, the information budget stays balanced. Facts inside aren't thrown away. They're recoded on boundaries and radiated out in scrambled form. Rendering isn't destroying alternatives. It's stabilizing one branch while weaving the others into correlations you don't access locally. Now fold in the firewall debate as a caution. If we push metaphors too literally, if we insist on a classical interior that everyone agrees on, everywhere, we break the books. Consistency lives in quantum structure. Who can ask which question, with what access, within which wedge? Boundaries are interfaces. Observers are instances with different entanglement slices. Smoothness for one doesn't guarantee naive duplicates for all. Here's the stake for our larger story. If horizons are information interfaces and the ledger never loses a line, then the cosmic horizon isn't a dead wall. It's a thermodynamic surface with a temperature and an entropy. The Gibbons, Hawking touch, quietly counting the states accessible to us. It bounds our patch's storage, sets our compression ratio, and suggests that what's rendered is whatever can be stabilized and redundantly recorded within our wedge. Past that, details aren't gone. They're just beyond retrieval for us, cached on a boundary we can't cross, or encoded in correlations our light cones can't collect. The horizon as interface, what's rendered, what's cached. While the black hole accountant tallies every bit, something quieter surrounds us all the time. A horizon that behaves like an interface. Not a brick wall, an API. What you can ask, what answers can return, and how much detail can ever be stabilized all depend on which horizon you mean and who you are when you ask. Start with the cosmological menu. There's the particle horizon, the farthest light that has reached us so far. There's the event horizon, the limit on what can ever reach us, even if we wait forever in an accelerating universe. And there's the apparent horizon, a locally defined surface where outgoing light rays hover at the threshold between expanding away and being dragged back by gravity. They aren't the same, and they're observer-dependent. Shift your motion, change your frame, and your apparent horizon shifts. The interface isn't universal, it's personal to your patch. Thermodynamics sneaks in. A de Sitter-like universe with dark energy has a temperature, the Gibbons-Hawking temperature set by its horizon scale. It also has an entropy proportional to horizon area. That's the boundary ledger talking again. Your causal patch carries a finite number of accessible microstates. The horizon radiates faintly as if it were a warm screen. It's not heat you can toast your hands on, but it's a physical bookmark that says, here's the edge of what you can access from here. Interpret that through the interface lens. Inside your patch, facts can stabilize because signals can circulate, redundantly encode, and be cross-checked. At the horizon, those facts meet a limit. Beyond this surface, correlations can't be fetched. So what S rendered? Anything whose records can be copied within your wedge, photons bouncing, fields interacting, memories written into matter. What S cached? The correlations that would answer finer questions if only you had access to the rest of the system. They exist in the global state, but from your standpoint, they're behind the interface and out of causal reach. Now add subtlety. The cosmological event horizon is global and future-facing. It cares about the entire expansion history. The apparent horizon is local and immediate. It cares about the flow of light right now. Observers following different world lines slice spacetime differently and disagree on what counts as inside. That isn't mysticism. It's geometry and causality. The interface offers different endpoints depending on the route you take to call it. Two users, different dashboards, same backend. Here's a micro story. An astronaut drifts far from any mass in a dark energy-dominated era. Their apparent horizon sits closer than ours did in the ancient past. Their sky is emptier. Their interface returns fewer endpoints. A cosmologist in our time points a telescope and strings photons across billions of light years. Same universe, different queries, different caches available. They aren't contradicting each other. They're making different API calls. Thermodynamics insists on stakes. Finite horizon entropy means finite recoverable detail. Try to pack more independent information into your patch than the area allows, and physics pays you back with heat, gravitational collapse, or decoherence that spreads and blurs until redundancy eats the surplus. The interface rate limits you. It won't let you exceed the bandwidth or the storage quota of your wedge. This is where caution matters. Saying horizons are interfaces doesn't mean a server flickers on when you look. It means what counts as a stable, objective record is constrained by which degrees of freedom you can entangle with and copy. No interaction, no redundancy, no objectivity. That's decoherence scaled up. The render isn't will. It's stabilization by broadcast within reach of your antennas. Bring back de Sitter temperature. A horizon with a temperature radiates noise into your patch, a bath that any detector, given absurd patience, would register. That bath isn't a bug, it's the signature of the interface's microstates. An entropy proportional to area is a storage rule. Your patch's total distinctness is bounded by the size of its edge. The world inside is richly detailed because most of those bits are tied up in redundant encodings of the same macroscopic facts. That redundancy is why we agree on chairs and stars. It's also why the finite quota isn't crippling. You don't need unique bits for every molecule's tail when the macrostory is the one you can test. Observer dependence without mysticism helps with collapse. When you measure, you're not commanding reality. You're joining the interface with your own degrees of freedom, becoming part of the redundancy network. The outcome you see is the branch your wedge can stabilize. Another observer with a different wedge can, in principle, reconstruct different slices of the same global state. No contradiction arises because no one can access all slices at once. Entanglement structure is the permission system. Light cones are the firewalls. Here's a human moment. A team simulates light propagation near a cosmological horizon and watches how information about a source dribbles into a detector over time. The signal fades into the bath, encoded in modes that stretch to the edge. They argue about whether the last bits ever arrive. The math says no, beyond the horizon, not for you. Someone sighs, writes cached elsewhere on the whiteboard and circles it. So the horizon as interface isn't a poetic flourish. It's a working model that ties together unitary bookkeeping, finite storage, redundancy, and latency. Your world is an instance bounded by your horizon, with a budget on how much can be stabilized and a rulebook for what can be fetched. Past that, details aren't non-existent, they're beyond your API. And that perspective sets up the next move. Let the micro, decoherence, einselection, entanglement, run on the macro stage of an expanding universe to see how rendering becomes everyday reality. When micro meets macro, decoherence at cosmological scale. We've been treating horizons like interfaces and information as the currency. Now let's let quantum mechanics run on the whole sky. The question is simple. Does decoherence, the environment picking stable facts, operate at cosmological scale? Yes. And when it does, rendering stops sounding mystical and starts sounding like bookkeeping done by an enormous environment. Start in the early universe. After inflation, the quantum ripples it stretched had to become the classical seeds we measure in the microwave background. That handoff is decoherence on a grand stage. The environment isn't a lab bench. It's the bath of photons, neutrinos, and gravitons, plus the self-gravity of the perturbations. Modes of the density field that would, in principle, have interfered, got entangled with countless other degrees of freedom and stopped talking. What survives are pointer variables. Classical density contrasts with definite phases that gravity can amplify. Here, S where einselection, environment-induced superselection, does the sorting. In labs, pointers are positions of dust motes and needle deflections. In cosmology, the robust basis consists of curvature perturbations with nearly Gaussian statistics and definite phases relative to the acoustic oscillations. Those are the variables the photon, baryon plasma responds to. Anything that would have required delicate phase coherence across horizon scales washed out. The universe didn't choose that basis because we like it. The environment imposed it. The timescales are vicious. Even tiny couplings across vast volumes add up. A primordial mode that re-enters the horizon interacts with a sea of particles whose number density dwarfs anything you can build on Earth. Phase information vanishes into correlations that, in practice, no one can recover. That's classicality by entanglement, not by decree. Consciousness never enters. Access does. Now look later when stars form and galaxies collide. Every macroscopic degree, gas density, temperature, angular momentum, couples to a ferocious environment. Photons scatter off dust, turbulence shreds coherence, magnetic fields and shocks mix phases. Decoherence times for macro scales are effectively instantaneous compared to dynamical times. That's why astrophysical structures have well-defined locations and velocities. The sky looks rendered because the environment floods it with redundant records. Quantum Darwinism sharpens this. Objectivity emerges when many fragments of the environment independently carry the same information about a system. A rock sitting in sunlight imprints its position on zillions of photons. Many observers can read the same story without disturbing the rock. The cosmos is the most generous Darwinist imaginable. The cosmic microwave background, starlight, dust emission, gravitational lensing, all broadcast overlapping, redundant encodings of large-scale structure. That redundancy is what makes your reality look stable to many different observers in different places and times. It's not a central server, it's a copy storm. Here's a micro story. A lab group tries to keep a superconducting qubit coherent for milliseconds. They fight stray microwave photons, phonons in the substrate, cosmic rays that flip bits. They succeed long enough to run a small algorithm, then lose coherence. Outside, a tiny galaxy tries to keep a delicate bar structure intact while bathed in the microwave background, bombarded by cosmic rays, stirred by satellite flybys. The bar persists because the macroscopic variables are pointer stable, the delicate phases don't. Same rule, different stage. If you're worried that this smears agency away, hold the line. Decoherence doesn't fix outcomes globally, It fixes them locally where information has spread. The universe computes context. Inside your horizon, within your light cone, facts become facts because records multiply. Outside, where records can't arrive, the fact is inert for you. That's observer dependence without mysticism. Each wedge stabilizes what it can redundantly store. There's a technical payoff in the early sky. The near-Gaussianity of the CMB isn't just an aesthetic. It's the fingerprint of simple initial conditions that decohered into a classical stochastic field. Small non-Gaussianities, limits measured to tight bounds, are precisely the kind of deviations you'd expect if the environment selection wasn't perfect or if inflation's pen had small features. The lack of large non-Gaussianity is the signature of ruthless compression. The environment chose a simple, robust basis and crushed the rest. And consider gravitational waves. A stochastic background from the early universe would be another channel carrying records, decohered by cosmic expansion itself. As waves stretch and redshift, they leave behind classical correlations that, in principle, pulsar timing arrays and space interferometers can read. Again, micro jitters become macro facts when an environment big enough and long-lived enough writes them down. Bring this home to collapse. In the interface picture, a measurement is just an entangling interaction whose products are redundantly copied through accessible channels. On cosmological scales, those channels are vast and patient. They write the same story in many places, in photon baths, in dust grains, in tidal fields. Once written broadly enough, you can't get the phases back. That's why cats aren't quantum and why galaxy counts don't show fringes. Here's the stake. You don't need a watcher to make the universe real. You need an environment with bandwidth, and you have one. The cosmic horizon bounds that bandwidth. Light speed meters it out. Holographic entropy caps the storage. Within that budget, decoherence and Darwinism select a world that looks crisp. What you call rendering is just the moment facts go from fragile amplitudes to robust, redundant records inside a finite wedge. What looks like a glitch, real constraints versus romantic myths. By now, the metaphor is tempting. See an odd galaxy at dawn, a giant empty patch, a cold splotch on the CMB, and it's easy to whisper glitch. But the sky punishes shortcuts. The cleanest stories are the ones that survive new data, not the ones that flatter our hunger for mystery. Start with JWST's early galaxies. The first wave of headlines loved the phrase "too big, too soon." Then spectra rolled in, photometric fits improved, lensing models sharpened, and many masses ticked downward. Not all some stayed hefty, but the panic softened into work. Star formation efficiency likely runs hotter in metal-poor halos than we guessed. Dust reddening and strong nebular lines confused early templates. A few show lensing magnification we missed on first pass. The correction isn't retreat, it's resolution. The universe didn't bend its rules to stun us. Our priors were coarse. That's how science handles tension. You look for systematics. You add missing physics. You check whether parameter shifts within the CMB and bow-allowed box relieve the strain. Lambdictum scaffolding holds because it's nailed to dozens of independent anchors. Acoustic peaks, lensing, abundances, bow scales, supernova distances. If one brand new window hints at a crack, you don't bulldoze the house. You inspect the window, then the frame. Voids tell the same cautionary tale. Boötes looks like a hole left by a lazy renderer, but simulations built from inflation's seed field produce similar yawning hollows, just rarely. Rare has a number. If the odds line up with the volume we've surveyed, you shrug and keep counting. If not, you ask whether the initial power spectrum needs a feature, still within inflation's playbook. Either way, emptiness isn't a bug. It's gravity drawing down contrast, leaving low information interiors that physics prefers because there's simply less to store. The CMB cold spot draws the loudest whispers. It's big, deep, and lonely. Is it an imprint of a giant supervoid via the late integrated Sachs-Wolf effect? Surveys found underdensity along that line of sight, but probably not enough to do the full job. Is it primordial, an exotic bubble collision, a feature in the inflattened potential? Maybe, but evidence is thin. Or is it a statistical tale in a Gaussian field? Also maybe. The truth is boring and honest. The significance depends on how you define your tests after looking. Cherry-picking a weird patch and then asking how weird it is always inflates drama. That's why blind analyses matter. They're the antidote to romantic myths. Pixel hunts come next. If spacetime were a grid, high-energy photons from distant bursts might disperse by energy. Precise interferometers might catch holographic jitter. Decades of clever experiments put tight upper bounds and found nothing conclusive. That null is a result. It's as if discreteness lives underneath. It hides behind symmetries and cancellations so strong that our baselines can't scrape it loose. Smoothness looks like compression, not like sloppiness. The absence of flicker isn't proof of a perfect continuum. It's proof that any granularity respects Lorentz invariance to painful precision. Here's a micro story. A conference coffee line buzzes about a preprint claiming energy-dependent photon delays from a gamma-ray burst. 2 months later, a reanalysis folds in instrument response and source intrinsic lags. The signal evaporates. The lead author presents the revised plot without hedging. The room doesn't groan, it nods. That's the culture you want around seductive anomalies. So what actually looks like rendering when you strip away wishful thinking? Compression behaving like physics. Decoherence killing phase information exactly where environments are thick. Redundancy making macroscopic facts objective while obeying a finite horizon storage quota. Holographic bounds whispering that surfaces count, so empty volumes don't demand bits. Lightspeed latency fencing off what can't be asked from what can. Everywhere you expect a cheap glitch, you find a costly constraint instead. There's a payoff in humility. A universe that selects stable facts through interaction doesn't need a central server or a watching eye. It needs bandwidth, boundaries, and time. Where surprises remain, odd morphologies at high redshift, a stubborn cold patch, an outlier void. The honest play is to thicken the model, not invent a programmer with a weak graphics card. Real constraints make cleaner stories than romantic myths because they keep paying rent as data accumulates. One more stake before we move on. Trust is a resource. If we hype every tension as a code tier, we'll train people to ignore real cracks when they appear. The better path is sharper. Weigh priors, chase systematics, expand the ledger only when the ledger insists. What survives that gauntlet is worth your wonder. And with that filter in place, we can finally ask what a compressed reality means for how we live inside it. Life inside a compressed world, meaning, agency, and limits. So what does life look like inside a world that favors compression, where horizons act like interfaces and redundancy makes facts real? Start here. Bounded information means partial knowledge forever. No matter how good your instruments get, your wedge stays finite, your bandwidth metered by light, your storage capped by horizon entropy. That's not cynicism, it's orientation. You work with local gradients, local signals, local leverage. You change what you can entangle with. Agency lives in that entanglement. When you act, you don't overwrite the universe. You join it, adding your body and tools to the redundancy network. You flip bits in matter and light that'll be copied outward. Photons scattering off a letter you signed. The heat your muscles dump into the room. The radio wave from your transmitter sailing to a receiver on the far side of Earth a fraction of a second later. Those traces become part of the stable history inside your horizon because they're broadcast and cross-checkable. That's the quiet meaning. Your choices become real when the environment agrees to carry them. There's a moral in that for responsibility. Compression doesn't let you shrug and say nothing matters. It raises the bar. Only what you stabilize matters. A promise kept is a pattern redundantly copied in behavior others can verify. A promise ignored is noise that never earns redundancy. Ethics in a compressed world is a physics of records. You can't wish your impact into existence. You have to propagate it. Now think about reachable versus unreachable domains. Climate policy is reachable. It operates inside our light cones and within socio-technical systems that respond to signals, laws, markets, infrastructure, shared narratives. A star's future 10 billion light-years away is unreachable. You can model it, predict it, but you can't send a photon that will arrive in time to influence it. That distinction isn't fatalistic, it's focusing. Put your energy where redundancy will amplify it. Cities, habitats, education, instruments that keep listening after you're gone. Here's a micro story. An astronomer proposes a long baseline radio array whose decisive data will come in 30 years. She's mid-career. She knows she won't lead the key analyses. She champions it anyway, writes grants, mentors students, argues through design fights. First dishes go live after she retires. The array hears a faint drift in pulsar ticks that tightens bounds on low-frequency gravitational waves. Her name sits second or fifth on a paper that a younger colleague presents. Was it worth it? In a compressed world, yes, because the array is a machine that stabilizes truths beyond any single life. She invested in redundancy. Living with latency is part of the ethos. Projects that matter take longer than your own coherence time. That's not poetic, it's biological. You decohere into memory in other minds, into traces in stone and silicon, into photons carrying your image from a photo album to a far antenna in 1,000 years. You're a localized process that can widen its echo. The cosmic cap doesn't shrink meaning, it frames it. What you build that copies well. Ideas that fit human bandwidth, designs that outlast fads, institutions that error-correct, survives. Curiosity thrives under constraints too. A noisy channel makes you better at asking questions. If your budget is finite, you spend it on experiments that reduce uncertainty the most. That's Bayesian living. You don't chase every shimmering anomaly. You design tests that squeeze priors where it counts. In practice, that's what the best labs and missions already do. They pick few, clear, falsifiable targets and accept that the rest will have to wait. There's room for all without myth. The horizon isn't an insult, it's a canvas edge. The fact that the microwave background's acoustic peaks encode a drumbeat from about 380,000 years after the Big Bang, that we can pull densities and angles and tilts from that pattern, is proof that compression can be generous. A handful of numbers tell you a story across 13.8 billion years because the universe wrote sparingly and let time elaborate. Your personal horizon is smaller and stranger. It's the set of people you can reach, the problems you can entangle with, the skills you can stabilize. You can widen it by learning languages, building tools, joining teams, traveling, publishing open data, teaching. You can narrow it by hoarding, by isolating, by chasing noise. In a world where objectivity is redundancy, collaboration isn't virtue signaling. It's the physical way facts become public. Choice still matters. Quantum Darwinism doesn't pick your goals. It only explains why some outcomes stick once chosen. Decide to reduce needless suffering and you can push that pattern into durable structures, public health, safety nets, rights that replicate across constitutions. Decide to ignore suffering and you'll still generate records, but they'll be self-limiting. Systems with feedback that disregard error correction collapse. Entropy doesn't care about intent. It cares about gradients and resilience. There's a humility that comes with the ledger. You won't glimpse beyond your cosmic event horizon. You won't reverse decoherence in a forest or pull Hawking quanta into a global decoder. Yet the same rules that fence you in also carry your voice. Every sunrise throws billions of photons off your face. Every message you broadcast joins a shell expanding at sea, a growing sphere of your choices. One day, another civilization, if it exists and listens, could intersect a faint ring of your signal and reconstruct a trace. You won't know. That's fine. Meaning doesn't require acknowledgement from beyond your wedge. Here's a closing micro-story before the last step. A kid stares at a dark field through a small telescope and counts galaxies, then loses track and just breathes. Years later, she writes code for a survey that catalogs weak lensing arcs, tightening constraints on dark energy. She'll never know whether the universe's acceleration comes from a simple cosmological constant or something stranger. But her pipeline lowers the noise, reduces bias, and makes the next measurement sharper. That's living well in a compressed world. Accept the edge, push the signal, leave the channel clearer than you found it. So no, the universe doesn't stop rendering when you stop looking. It keeps computing within horizons, with or without you. The part that's yours to steer is what you make redundant, what you turn from private amplitude into public record. In a finite, latency-bound cosmos, that's how agency cashes out. You choose what gets stabilized. We live inside a patient ledger, where horizons set budgets and redundancy makes truth travel. The wonder is that finite rules still let meaning scale, and your choices become real when you make them copy. If this clicked, subscribe for more untold cosmic stories. Watch next, our deep dive on dark energy as the universe's ticking horizon. And if black hole bookkeeping grabbed you, cue up our feature on the page curve and how information fights its way back. Share this with someone who needs a bigger frame and drop the wildest, rendering question you want tested next.